My name is Jessica Webster, and this is my motion of falling objects video lab report. Here you can read my main objective and main result. My object under observation or system is a cup. Here you can see that my video is calibrated based on a 1 meter stick. The cup starts at the origin because that's where it was dropped and moving in the negative y direction. The initial time begins when there's no longer a contact force on the cup, and it ends when the cup hits the floor. This happens at 0.567 seconds. The video is using a frame rate of 30 frames per second. Here are the fundamental principles that we are basing our analysis off of in this lab. Keep in mind that for these two forces, the gravitational force and the drag force, only the y component of the vector will be affected, because we are just dropping the objects. Based on what case I'm looking at, this code may change a little bit. By that I mean whether I'm looking at a slow or fast moving object and whether I'm accounting drag force or not, but my initial values are constant. That's that the initial velocity and initial position start at 0, and the delta t I'm using is 0.001 because the computer can handle these computations in a timely manner. Also, you can see that I highlighted the velocity and position update equations. Because of the force, the velocity is going to increase while the computer is going through the while loop, and because of the velocity, the position is also going to continuously be increased as well. Also, for the heavier object, because of some sort of technical error, my acceleration was actually 10% higher than it should be. So just for simplicity's sake, I went ahead and updated this in my Python code. Here are my results for my fast-moving object without drag force accounted for. As you can see from the red line or my predicted data, this fits my observed data pretty well, which shows you that drag force didn't have much of an effect on my object. Here's my results for my fast-moving object with drag force accounted for. My B constant here was about 0.002, which shows you that it really didn't have a substantial effect on it. On the subject of my B value, I chose this based on what would best fit my data to the observed data. My next observation of analysis is a paper ball. I set up the axis so the motion would begin from the origin moving in the negative y direction. As I stated earlier, the initial time begins when there is no longer a contact force on the ball, and the final time is when the ball hits the ground. The frame rate in this video is 24 frames per second, and the final time is 0.541 seconds. Having only gravitational force accounted for my slow-moving object does not make for a good prediction for my observed data. Clearly, there is another force interacting with my object. With just the gravitational force, the prediction is that the paper ball falls much farther than it really does, and at a much faster rate. Here are my results for my slow-moving object with drag force accounted for. If we compare this to the graph that we just saw, you can tell how much of a difference the drag force makes in this object's movement. With a nice size B value of 0.72, my predicted data now fits my observed data pretty well. If we compare this graph to the fast-moving object with drag force, we can see how much of a difference the size and mass of an object make with how much drag an object gets when falling. For our what does it mean question, we want to see whether my slow-moving object reaches terminal velocity with or without drag force, or whether it does it all really. Graphically, we can conclude that my slow-moving object with drag force accounted for does reach terminal velocity. As the velocity increases, so does the drag force. And when the drag force is equal in magnitude to the gravitational force, this is when terminal velocity happens. If you look on the graph, when the line is straight, we know that the object is moving at a constant velocity. This also means that the net force equals 0, and the object has reached terminal velocity. If you look on the left where only the gravitational force is accounted for, you can see that the velocity is still increasing. Therefore, it has not reached terminal velocity. If you look on the right, where drag force is accounted for, you can see that the object has reached terminal velocity and it is moving constantly at that. What if there is an initial downward thrust on my slow-moving object? As you can see on the left, even with an initial velocity, there is no terminal velocity reached without a drag force to balance out the gravitational force. However, if you look on the right, with the drag force accounted for and an initial velocity, you can see that the object reaches the terminal velocity a lot faster than it did without. Thank you so much, and I hope you enjoyed my lab report.